I'll start
Oh,
recording while you do that.
all right, got it. Let me get my stuff up. I just got off work.
Well, welcome to office hours.
Thank you, thank you.
Glad you made it.
Mhm.
I'm going to put the camera on the paper. Hang on.
Sure.
Okay, we're recording. And here we go. Is that focus okay?
Yeah, that's good.
Great. So what would you like to talk about?
Um, we could talk about proof by cases.
Okay, proof by cases. We've seen several different examples of proof by cases. We've seen a proof when, D is 2, and then by the QR theorem, let's say that n is an integer, and that's the setup. So by the QR theorem, we know either n equals 2q, remainder 0, or maybe n equals 2q plus 1. This is with q and z. So we set up the cases at the top, and then we write, case 1, whatever it is, and then case 2, whatever it is. Okay. But it might be that we have a different divisor from 2. We could have a divisor of uh, d equals, well, we had a homework problem where n was in z and d was 5.
Yeah.
And then the result we wanted to show was about n squared. But the main mistake people made was they didn't write all the cases. They only wrote 3 of the cases. But there's going to be 5 cases because the divisor is 5. So either n equals 5q or n equals 5q plus 1 or n equals 5q plus 2 or what's the next case?
NQ plus 3 and NQ plus 4.
Yeah, and 5q plus 3 or n equals 5q plus 4. So we have 5 cases, even though what we wish to show is that n squared either looks like 5k or n squared looks like 5k plus 1 or n squared looks like 5k plus 4 in each case. So even though there are only 3 possible ways that n squared could wind up looking, we still have to prove it for 5 different cases for the original integer n, because we don't know what n is. N could be 7, in which case n has the form 5q plus 2. But n squared is going to wind up looking like 5k plus 4 in the case that n is 7, or maybe n is 8, right? And if
Mhm.
n is 8, n squared is going to wind up looking like 5k plus 1, even though n looked like a multiple of 5 plus 3. So the main thing to understand is that whatever your divisor is, that's the number of cases that you have to write. Okay.
Mhm.
So was there a particular proof by cases that you needed help on, or just sort of just a general idea of proof by cases?
Just a general overview. There wasn't really a specific one I needed help on. I just want to freshen up.
Well, it could be that D is 3. It might be some result where we're saying that like the product of 3 consecutive integers is divisible by 3. That was one of the examples that we did. Another example that we looked at was that if we divide a perfect square by 3, uh, we're never going to get a remainder of 2. So, uh,
Can we go over that one?
yeah, we still have 3 cases though, even though n squared can never look like 5k plus 2 by the QR theorem, we we know that either, well, D is 3. So you tell me, what are the different ways n could look if we're dividing n by 3?
N
Instead of
equals,
5q or 5q plus 1 or 5q plus
it'd be,
2.
it'd be 3Q,
Mm-hmm.
uh, 3Q
Or,
plus 1,
mm-hmm.
or 3Q plus 2.
Right. So we still have three cases that we have to investigate because we don't know what the integer n is. You
Yeah.
know, if n is 5, it looks like 3q plus 1. But this was the case where if n is in z, the result was then the square of n squared, either looks like 3k or n squared looks like 3k plus 1, where k is in z. So the result we want to get is about n squared. And it says, hey, when you divide n squared by 3, you're never going to get a remainder of 2. But n is some unknown integer, and a third of them are going to leave a remainder of 2 when we divide them by 3. So we have to write it in 3 cases. So we start the proof by just giving ourselves an integer n. Let n be an element of z, or you could say assume n is in z. And then we set up our 3 cases. By the QR theorem, we know this, or this is going to happen. Either n is 3q, or n is 3q plus 1, or n is 3q plus 2, where q is an integer, because a third of the integers look like this, a third of the integers look like this, and a third of the integers look like this. In every one of these 3 cases, we want to look at n squared and show n squared turns out looking like this or
Okay.
this.
Yeah.
So do we need to write some of those cases?
Yeah.
Okay. All right. So, hey, Bryce, we're looking at proof by cases. And the statement that we're going to try to prove by cases is that if n is an integer, then n squared either looks like 3k or n squared looks like 3k plus 1. What that's really saying, folks, is that when we divide a perfect square, that's what n squared is. It's a perfect square. When we divide a perfect square by 3, we're either going to get a remainder of 0, in which case n squared is going to equal a multiple of 3. It's going to equal 3k. Or when we divide n squared by 3, we're going to get a remainder of 1. And you can just think about the perfect squares, like 4 is a perfect square. Right? 4 is 2 squared. When we divide 4 by 3, what remainder do we get?
1.
Yeah, we get 1. What's the next perfect square after 4?
Once again. 9.
9. So when we divide 9 by 3, what remainder do we get?
0.
Yeah, so 9 is going to wind up looking like 3 times some integer. What's the next perfect square after 9?
16.
Good. So when we divide 16 by 3, what remainder do we get?
1.
1.
1. Good. What's the next perfect square?
25.
When we divide 25 by 3, what remainder do we get?
1.
Good. Let's do one more. What's the next perfect square after 30,
36.
after 25?
36.
36.
36. When we divide 36 by 3, which remainder do we get?
0.
0. And it turns out you can look at any perfect square you like. If you divide that perfect square by 3, you'll never get a remainder of 2. You'll only ever get a remainder of 0 or a remainder of 1.
Mm.
But when we set up the proof, we have to apply the QR theorem with d equals 3 to the original integer n. And since we don't know what integer that is, we have to look at the possibility that n is equal to 3q, or n is equal to 3q plus 1, or n is equal to 3q plus 2, because we don't know which one of these is actually true. So for case 1, we assume or suppose that n is equal to 3q, where q is in z. And what we want to do is say something smart about n squared. So we look at n squared. Well, n is 3q, right? So we'll square 3q. And what's that, 9q squared?
Yep.
Yep.
So which one of these two possibilities is n squared going to wind up looking like?
What's gonna end up looking like n squared? The first part.
Yeah, it's going to be a multiple of 3. It's going to be 3 times 3q
3q
squared.
squared.
Mm.
Right. And that's our m. So we talk about why 3q squared is an integer. Since q is an integer and products, because we're just multiplying to make 3q
Positive
squared.
integers.
Yeah. And products of integers are integers. We can call this thing m. M, which equals 3q squared, is actually in the integers. So n squared has the form, I could call that k, I suppose, since k is what's in, I'll call this thing k. Because it's called k here. K equals 3q squared. So n squared equals 3k, where k is in z. Thus, the statement that the conclusion we wanted, which is that n squared equals 3k, or n squared equals 3k plus 1, where k is in z, is true. So in case 1, when n is a multiple of 3, n squared winds up being a multiple of 3. But we've got 2 more cases to look at, because maybe n looks like 3q plus 1, or maybe n looks like 3q plus 2. In both of those cases, when we look at n squared should turn out to look like one of these. Let's try the second case. What should we suppose for case 2?
Case two. I suppose n squared equals
Careful,
3.
careful. We set up
Oh,
our
excuse me,
cases
excuse me.
based on n.
You're right. My fault.
That's all right.
All right, I was about to wish.
See, this helps. It helps to go back and look at what the QR theorem
Oh,
says about the cases.
so what is it? My cases. PF.
See, we just did the case when n equals 3q. All right, we got that one because we got that n squared looked like 3k. But what if n looks like 3q plus 1? Let's do that case. So what should we suppose?
Suppose by the QR theorem,
N equals what?
n equals 3q plus 1.
Yeah, we still wish to show that n squared looks like this or this. So let's go ahead and square it.
Yep.
So n squared is now 3q plus 1, quantity squared. Oh, well, that's 9q squared plus 6q plus 1. Which of these two is n squared going to wind up looking like?
The second one. The second
Yeah,
part. Yeah.
it's going to wind up looking like the second one. So let's go ahead and finish that. So this is going to be 3 times the quantity 3q squared plus 2q with this plus 1 hanging off the end. So this is going to turn out to be our k, right? So we just go ahead and say it. Hey, since q is in z, and what are we using? Sums and products?
Some of them products of integers are integers.
Yep.
EQ. Mm.
Then we go ahead and identify k. It's the stuff in parentheses. It's 3q squared plus 2q. And we go ahead and say, hey, that is definitely an integer because sums and products of integers are integers. So, this statement that n squared equals 3k, well, actually, in this case, what is n squared? Let's write what n squared starts looking like in this case.
Since Q is, sorry, I'm catching up.
See, in the first case, n squared wound up looking like 3k, right? But what's going to happen in this case? Well, take a look. What's n squared looking like?
N squared is looking like, oh, it's three. Three
Three.
Q. It's our 3Q squared plus two. Plus 2Q.
Yeah, but we're calling this thing k.
Okay, excuse me, yeah.
So n squared equals 3k plus 1 with k and z in this case. But we have satisfied this OR conclusion. The OR conclusion is satisfied if we get n squared looking like 3k
Mhm.
or if we get n squared looking like 3k plus 1. We happen to get it looking like 3k plus 1. So we can just say thus n squared equals 3k or n squared equals 3k plus 1 is true. So we killed it in case 2. When n looked like 3q plus 1, n squared wound up looking like 3k plus 1. What's the third case?
3Q plus two. Or the third case is that Rn is going to equal 3Q plus two.
Yeah, our n is going to equal 3q plus 2. The remainder is 2. So we have to treat that case, even though it's not one of the things we want n squared to look like. It's certainly something that n could look like because a third of the integers look like this, like 5, 8. What are some other integers that give a remainder of 2 when you divide them by 3 besides 5 and 8?
14.
Yeah, 14 is 12 plus 2, so it looks like 3 times 4 plus 2. Good.
Mhm.
So there's a whole bunch of integers that could look like 3q plus 2. Well, it's fine. We're still going to get our result about n squared. So here we suppose that n equals 3q plus 2, where q is in z. We're still going to be able to figure out that n squared looks like either this or this.
That.
So, yeah, my point is you got to be careful. You cannot just treat the cases about the result, which is about n squared. You have to understand that n could be any one of these, even if n squared can't. Now let's look at n squared. Well, n is 3q plus 2, so we'll square that. What does that become when we square that?
We squared, that becomes 9Q
Squared.
squared plus 4.
See, what's 3 times 2?
3 times 2 is 6.
So we got 2 of those. So that's
Yeah,
12q plus, and yeah, and there's going to be a 4 hanging off the end.
before then.
Now, this is our n squared. Is it going to wind up looking like this or like this?
It's going to end up looking like the second one.
That's right, because 4 is really 3 plus 1, isn't it?
Yeah, when we factor out 3, then it would just be 3 plus 1.
Exactly. We'll be able to factor out a 3 from this, this, and this plus 1 is what's left over from the 4. We basically applied the QR theorem to 4 to get it looking like 3 times 1 plus 1. So we pull the 3 out, and we have 3q squared plus 4q plus 1. That's going to be our k. Whole thing is plus 1. So n squared equals, oh, we got to talk about why k is an integer. I forgot. I
Yep.
almost forgot. Why is k an integer?
K is an integer because sums and products of integers are integers.
That's right. Since q is in z and sums and products of integers are integers, we can say k equals 3k q squared plus 4q plus 1 is in fact in z,
See,
right? So n squared equals 3k plus 1 in this case. In every case, we got n squared looking like either 3k or 3k plus 1. We got it in every single case. Even in the first case, we got n squared looking like this. So that means either n squared looks like 3k or it looks like 3k plus 1. So in all three cases, we got the result that we wanted. So that's kind of the deal with proof by cases. Do you want me to give you a do later to work on to
yep,
prepare for the test?
yes, ma'am.
Okay, so do later. Call this one that we just did. Example one. That if n is in z, then n squared looks like this or this. This was example one.
Mhm.
So now this will be example two. I just want to keep myself organized. Proof. If n is in z, then uh, n squared plus 5n minus 7 is always odd. So what is going to be the divisor in this particular do later?
And n squared plus 5n minus 7 is always odd.
Yeah, we're saying something's always odd. So when we're talking about something always being even or always being odd, what's really the divisor we're playing with?
2.
Yep. So D is 2. And so the QR theorem setup is going to be that N equals 2Q
Q
or,
or n equals 2q plus 1.
yep. So there'll be two cases, right?
Yeah.
And in both cases, when you look at this expression, you know, I mean, yeah, n has two different ways it could look. It could look like 2q. See, n can be even, but this expression is going to wind up to be odd. N could be odd. Well, that expression n squared plus 5n minus 7 is still going to turn out to be
Yeah.
odd. See what I mean? So, I
Yeah.
mean, we didn't question it too much that we had to write two cases when the result could only look like 2k plus 1,
One
right?
either, yeah.
But later, when we get something more complicated, like this statement in example one, we get confused because we see something about n squared looking like 3k or n squared looking like 3k plus 1, and we accidentally forget that that doesn't mean n can't look like 3q plus 2. See what I mean? So that's the main problem students happen to have. Hey, Divine, with proof by cases.
I see what you're saying. That's sneaky though, because you don't rely, sometimes you don't really pay attention to the question.
Yeah,
Or
you
you
don't
just
really
basically
see.
read it because you won't know how many cases. Like, and the other, it's kind of like what the case are, what the cases are going to be. Right.
Yeah,
This
but
one,
you,
you
but
pay
we,
attention.
I've tried to tell you, hey, if the result is that something's going
Uh,
to turn out to be even or odd,
so one
we're
or the other,
we're
just two.
definitely dividing by two. Yeah,
Yeah.
so there's going to be
Yeah.
two cases.
Makes sense. All right,
So
cool.
Bryce, do you have a particular question since you've come in second?
Yeah, I was gonna ask about particularly like the calculator situations. Are they more for factoring, those factorization questions?
Yeah, for like standard factored form.
Okay, and the what about the mod questions
Mod questions, you don't use a calculator. Mod questions are always worked by hand. Shall
by
we
hand?
do an example of a mod question?
Yes, please.
All right, so let's suppose that A mod 10 is 6 and B mod 10, the mod has to be the same for us to play it. So 10, they both have to be mod 10. We're dividing A by 10, getting a remainder of 6. We're dividing B by 10. I don't know, let's say we're getting a remainder of 7. Okay.
Okay.
Find A plus B mod 10. And then we could also try to find AB mod 10. Or we could make it more complicated. We could say find, I don't know, 3AB mod 10. Okay. The point is, we get equations based on the definition of mod. Basically, A mod 10 means, okay, so A mod 10 equals 6. That gives us an equation. It tells us, hey, A is some number of copies of 10. We don't even know. We don't even care. We can just say 10 times, I don't know, Q1. But
Okay.
But the point is the remainder is going to be 6.
Okay.
Mm-hmm. And B mod 10, what did we say that was? 7? So can you give me an equation for B based on that?
B equals 10Q2
Mm-hmm.
plus 7.
Right. So once we have these equations, then we can investigate A plus B.
Okay.
We just substitute in, oh, A is 10Q1 plus 6.
Right.
B is some number of copies of 10. We don't even care. What we really care is that remainder is 7. So now we add these up. It's just arithmetic. So it's 10Q1 plus, I'll put the Q1 and Q2 up front, plus, well, what's 6 plus 7?
13.
Right. But the divisor, well, do you see that? What is the divisor when we say something mod 10? What are we really dividing by? Dividing by
Yeah,
the 10, because
yeah.
it's A mod D. So the divisor's right here. It's the 10. So we're dividing by 10.
Okay.
So 13 is too big of a remainder if our divisor is 10, and our divisor is 10 because we're working mod 10. So we just split 13 up. We apply the QR theorem to 13. How many times does 10 fit into 13?
Just once.
Yeah. And what's our remainder when we
3.
divide? Yes. So the point is now we can
Okay.
pull a 10 out of everything except the plus 3. And this is an integer. This is in Z. So it says A plus B looks like 10 times some integer plus 3. What we really care about is the fact that there's a 3 as a remainder when we divided A plus B is equal to 10 times K plus 3. And so then we use, the equations backwards. Once we have the equation for A plus B, we can go back and say, oh, that means A plus B mod 10 is the 3. So we
Huh.
use this
Okay.
equation back and forth. K
But
is
I
equal to,
see it all goes back to finding out that we're gonna find a K for some integer. Like we're
that's right. We're trying to find, and what we really want is to get our eyeballs on the remainder after we
right.
found the K by factoring out as many copies of 10 as possible.
Right.
Right. So let's do the second one. In the second one, we're looking at 3AB. Okay, can we still see our equations up there? There they are.
Yeah.
So 3AB is going to be 3 times A times B. Okay, so what was A? We have an
10
equation.
quadrant 1 plus 6
10Q1
or
plus
Q1.
6. And then B, I'm just using Q1 and Q2. We could have used
It's just like a
integers.
variable.
Yeah, we could have used K and J. It'd be fine.
Okay. So then this
B,
was 10
yeah,
Q2 plus
10Q2
7.
plus 7. Now we got to actually do some algebra. Okay, so 10Q1 times 10Q2 is 100 Q1 Q2, the first times the first. Then the outers, what is that? 70
70, yep.
Q1, the inners,
6B.
Q2, and then the lasts. And we still have to multiply through by 3. So let's see, we got 300 Q1, Q2, plus 210 Q1, plus how many Q2s do we have when we multiply 60 by 3?
180.
Okay, 180. And then 3 times 40 is 120.
Yep.
3 times 2 is 6. So this is 126.
Mm.
Now, the mod is 10. Okay, we want to find 3AB mod 10. Okay, that's what we're looking for. So we have to divide by 10. The divisor is still 10. So we can take a 10 out of 300. We can take a 10 out of 210. We'll be able to take a 10 out of 180. We can take some 10s out of 126 and we'll
Yeah.
have some leftovers. How many 10s can we take out of 126? Basically, we're going to apply the QR theorem to 126. with D equals 10. So how many copies of 10 fits into 126?
12.
And what's our leftover, our remainder?
6.
Yeah, and see, this is going to turn out to be
That's the
our
remainder.
answer.
Yeah.
Because now we can pull 10 out of 300, leaving 30, Q1, Q2. When we pull 10 out of 210, what's left? 210, Q1?
Oh, 21.
Yep, because just the zero went
Just the
out
zero.
here,
Yeah. Yeah.
right? And then when we factor out 10
That's
from 100,
18.
18 Q2. When we factor the 10 out of 10 times 12, well, it's 10 times 12. So the 10 is out here, the 12 is left in there,
Yeah.
plus 6. This is
Yeah.
that's an
Yeah.
integer. And now we
Okay.
go backward. And what is 3AB mod 10?
Is this 6?
Yep. So it actually happens to be the same as A mod 10. They're both 6. They're
Okay.
different numbers, but they both yield a remainder of 6 when
Yeah,
we divide
I
them
can see
by
the flow of
10.
it now.
Yes. So you want me to give you one to do later?
Uh, yeah, I just need to find something right.
Yeah, I did that whole thing in green. I don't usually do that. All right, so suppose A mod 9 is 5 and B mod 9 is 4. Find A plus B. How about we do this? A plus 2B
Okay.
mod 9, and then find A squared B mod 9. So it's just a little bit different algebra. You're still going to plug in an equation for A, but it's going to be a mod 9 equation because D is 9. You're going to plug in an equation for B. It's going to have a 9 in it, like 9Q2 plus, I don't know what, 4. And then you add the equation, you double the equation for B. Basically, you just go through the algebra and figure out what this is and reduce it mod 9. And you can do the same thing for A squared times B. Don't let it scare you. Just try and do it. Just
A
try
little bit.
to just try and push through the algebra. But see, this is Sunday night, right? You can ask about this. You can ask for a pop-up office hour, or you can come. I've got office hours tomorrow in my office
Okay.
in Yorker Road, 345. I've got office hours on Tuesday night from 5 to 6 live in my office. So, or you can just email me and ask me to look at your work, and I'll be glad to look at it and tell you if it's right.
I can show you it tomorrow for sure. I'll be working on it.
That sounds good. Divine, do you have a particular question? It's your turn now that you're here.
Yes.
Great.
So my question is, for the test we have on Wednesday, is it just the factorization we need to worry about and the mod?
Gosh, no.
Oh,
That's just stuff from one section. In fact, that's just the end of section 4.4. You need section 4.1. So for test 2, section 4.1 and section 4.2 was the intro to writing proofs and also disproofs. And the key was, is the statement existential or is the statement universal? And if it's existential, we can use an example to prove it, right? Cook up
yes.
an example, verify X, whatever the X is that you cook up, that it's really in the domain. And then you verify that the property, whatever the property is you're trying to prove, holds for X, right? But if it's universal, like for all X in D, if P of X, then Q of X, as opposed to existential, which is there exists an X in some domain, such that P of X, okay, they're two entirely different kinds of statements. We have three proof methods for universal, but we cannot use an example.
Okay. Also, it's for universal that we have to do the scrap work and everything.
Well, actually, we usually do scrap work for an existential because we're looking for an example. I'm glad you asked that. See, we usually do the scrap work to figure out what example X, we found that works, right? But in
Yes.
Universal, we don't generally do scrap work. We use variables and definitions, algebra, and things we may assume without proof, like closure properties of the integers, like sums of integers or integers, and uh, the zero product property. But we had three proof methods: direct proof method, where for direct proof method, we assume the hypothesis P of X, and then we wish to show that the result Q of X follows, right?
Yeah.
Or we also had proof by contrapositive, where we're basically proving the contrapositive of if P then Q. So we assume not Q. And what do we wish to show?
Not P.
Not P. Great. So that's two proof methods. And the last proof method, which is sort of the most interesting in some sense, if we're
The
trying to,
contradiction.
yes, proof by contradiction. What do we assume in proof by contradiction?
Um, so I think we assume the hypothesis, we are assuming the hypothesis,
Well,
right?
what is the hypothesis for proof by contradiction, though?
So
It's
we have to first get the contrapositive first, then we have to then assume the hypothesis is, I've forgotten how you explained it in class on
okay. So
Thursday.
contrapositive is a whole different proof method than proof by contradiction. They're not the same proof method. Proof by contradiction, we assume the negation. In other words, we assume, well, the negation of there exists is there for all is there exists an X in D. And the negation of if P then Q is that P happened and Q failed. This is what you assume. You
Okay.
assume the negation, and then we get a contradiction. And then we conclude the original is true because the negation leads to a contradiction.
Okay.
So the negation can't possibly be true if it leads to something impossible. And then
Okay.
the logic behind proof by contradiction is, the way we find that the original is true is by showing that the negation's impossible. And the definitions that we need for both kinds of proof, let's just go through our list of definitions that we need. We learned even and odd, right?
Um, prime, perfect square and perfect cube.
Yeah, prime and composite, and perfect square and perfect cube. And we learned divides.
And mod.
And we learned rational. And we learned A mod D and A div D, although we don't use A div D so much in proofs. We learned the QR theorem to set up cases. Any other definitions that we learned? I wonder if we're missing anything.
No, I don't think so.
Okay, and then we also need to know standard factored form and then the A mod D and the A div D. So it's going to be numerous proofs. There's going to be a standard factored form type problem. And so up here we said, section 4.1 and 4.2. You really should read this section. If you haven't done it, you should read 4.2 in the book. But section 4.3 was rational. Oh, and then rational versus irrational and irrational. There were some proofs that involved one rational and one irrational, and there's even a special topics video on that. Section 4.4 was divides. Section 4.5 was proof by cases and the QR theorem. And then section 4.7 and 4.8 was methods of proof that aren't direct, so indirect proof methods. So that's a lot for one page, but that's that here. So
Okay.
that kind of, I mean, it's plenty. It's plenty to learn.
And oh, sorry, you were
Go ahead,
saying?
go ahead, go ahead.
I'm saying, like, where do we find the videos? Because I know I missed a couple things you said before I joined, and I've been trying to see where I could find the videos you upload about the
All right, let me help you. Can you see my screen?
Yes.
All right, let's go to my YouTube channel. This is my YouTube channel. It's Liz Good 2766. Now I can
Yes.
see more than you can see, okay? Because I got lots and lots of playlists that are private now but we've got office hour videos. Those are up.
Okay.
Okay. There's some 263. I think there's a short lecture in there, some discrete math shorts. And then there's special topics. Like you're seeing a lot of stuff that that only I can see here. But there's like a special topics here. Yeah, special topics on functions playlist. And in
The floor
there.
and ceiling function are
Oh,
used in computer
no,
science
that's not
to
mine.
round to the nearest integer. Notation for the
Sorry,
floor is outlined in
sorry.
yellow, while the notation
Ah.
for the ceiling is in red.
Sorry. These are just some cool videos that I don't know, on all kinds of stuff. But my videos, my playlist, I've got some pre-recorded videos. That's private. Anyway, when you go and just look at my playlists, you'll see what you can see, okay?
Okay.
And you'll see, and the ones that are like my handwriting, you'll see.
Okay.
Okay, so
Thank you.
definitely discrete math office hours from fall 2025. There's some really good videos in there because people have asked some really good questions. And like tonight's video will be up in office hours. If you came in
Okay.
late and missed something, you can look at the beginning of the video.
Okay.
But
Thank
my
you.
YouTube channel, the link to it, it's in the reading page. Did you know that?
Yeah, no, I know that, but I thought that you were going to upload it on like the Zoom when I went on the
No,
Zoom,
no,
this
no,
thing.
no, 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 no. I don't upload them to Zoom. I don't upload them to Blackboard. That's you just got to go to my YouTube channel, okay?
Okay.
I'm glad you asked. Other questions?
And could you go over the proof by contrapositive? Like,
Sure,
could you give an example of that?
sure. All right. I'll give a couple of them. Gosh, there's a terrible glare here. Let me put this down. The glare is just off. Sorry. So on a proof by contrapositive, here's one example. Proof. if 5x squared is even, then x squared is even. Now you can actually prove that directly using unique factorization, but it's easier and for some folks just to prove it by contrapositive. This is our p of x, and this is our q of x, and this is universally quantified. It's for all integers, for all x and z. So the contrapositive, let's write the contrapositive. So the quantification on this is a for all. What's the quantification on the contrapositive, Divine? All right, let me ask you this. Is the contrapositive an if-then statement? It is. The contrapositive is an if-then statement. So it's an if-then statement, and that means it's universal because all if-then statements are universal. That's why
Oh,
it's called.
sorry, I didn't even know my mic was turned off.
Okay, so can you tell me what the contrapositive of this?
So I know it's supposed to be not Q of X, then not P. So
Good.
if X square is even, if X square is odd, sorry,
Yep.
then 5X square is odd.
Okay, so great. So you would just assume x squared is odd, right? Assume this. And then you would,
Then I will show that 5X square is odd.
sorry, I need to make this x. Let me make this just x.
Okay.
If x is odd, then yeah, your wish to show that 5x squared is odd. And that's easy to do. I mean, I'm assuming you can you apply the definition of
Yes,
odd.
then
Yeah,
by definition of odd, then we have to then use the SF, this standard factorization to factor it out, then prove it, then state the reason why the wait. For contrapositive, if we have when we get to the final answer, if we had like how do I say it? Like since by definition this is the by definition since no let's say since x plus
why don't we prove it?
okay,
That's
because
cool.
I'm trying to say something but I don't know how to put it in word.
You're going to use the definition of odd, but it's not necessarily called standard factored form. It's the QR theorem applied to an odd integer. I mean, that's what the definition of odd is. It's that it looks like 2k plus 1. So we're going to assume x is odd, okay?
Okay.
And what do we wish to show?
Um 5x square is odd.
Yeah. So now it's the definition of odd by the, right? We used the definition of odd. And this was, we learned about even and odd before we learned about the QR theorem. But when we
Yes.
learned the QR theorem, we realized, I hope, that even and odd means we're just dividing by the divisor d equals 2. And if something's odd, we're saying, hey, when you divide x by d equals 2, you're going to get a remainder of 1. That's what the definition of odd says. X looks like what if x is odd?
So that's 2k plus 1 for some integer k.
Yep. For some integer k, or where k, you can say it that way, or where k is in z. And so what do we wish to show? Let's dig into our wish. What do we really wish?
Wish to show that 5x square is odd.
And so what would it look like? What would make it look
So
odd?
so that's gonna be 2j plus 1 for some integer j for some j and z.
Yep. I'm doing it your way and you're doing it my way. That's good. So great. We have an equation for x. Because it was odd, we know it looks like this, and we know something about k. And now we want to say something smart about 5x squared. And that's the nice thing about putting the wish down a little deeper. investigating that wish, that helps us realize, oh, okay, we got to look at 5x squared. So let's look at 5x squared. So tell me what to write.
So there's gonna be 5 in parentheses. X is 2k plus 1. So that's gonna be 2k plus 1, then raised by 2. What
Great.
happened to the judge and the 2j plus 1?
That's just a wish.
Okay.
We don't know that. We're shooting for that. Okay. That's what we're trying to get. See what I mean? There's a difference between what we have in our hand, that X is odd, and what we wish to show. So this is our job, is to show that this happens.
Okay.
We get to use this money, that X is actually odd. So let's square 2k plus 1. What do we get when we square 2k plus 1?
That's 4k squared plus 4k plus 2,
1 times 1 is 1.
1, sorry.
No problem. Now let's multiply the 5 through. We have 20k squared plus 20k plus 5.
Plus 5.
And we're trying to show that it looks like 2 times some integer plus 1. So we have to deal with this 5.
Factorization. So then it's gonna be 5 is
Yeah, we're going to divide 5 by 2. What does 5 look like when we divide it by 2?
that's gonna be 2 mod 1.
Yeah, it's actually 1 mod 2. It's 2 times 2 plus 1.
Oh, okay.
5 is equivalent to 1 mod 2. The mod is the divisor. The modulus is, anyway, here it's a little confusing, the nomenclature, but we're dividing by d equals 2, and we're getting a remainder of 1. So now we can pull a 2 out of everything here, and we'll have a plus 1 left over. And what's going to be in here?
So that's gonna be 10k raised by 2 plus 10k plus 2.
Yep, and then this is our j. And so we go ahead and say, hey, since k is in z, we use this money now that k is in z. Since k is in z, and sums and products of integers are integers, because this is being built by adding and multiplying, sums and products of ints are ints, j equals that whole thing is definitely in z, right?
Yes.
So 5x squared winds up equaling 2j plus 1, where j is in z. We got both part 1 of the definition of odd and part 2 of the definition of odd, which makes 5x squared odd by definition of odd, and we did it. Okay, that's one kind of problem that would be.
So we don't have to write that the original is false or
No, because we never assumed that the original was false.
okay.
It's proof by contrapositive, not proof by contradiction. Shall we write a proof by contradiction of the
Yes.
original? All right, let's
Yes,
try.
please.
All right, let's look at that. Because when we write a proof by contradiction, we will assume the negation. Contradiction. I want to write a proof by contradiction, my bad. So we assume the negation, and then we show that that leads to a contradiction. All right. So in a proof by contradiction, we're going to assume the negation. So help me with this. When we negate a for all statement, what kind of statement do we get?
There exists.
So
There exists an integer Wait. There exists an integer 5x.
Uh-uh,
Oh. There exists an integer x
such
such
that,
that 5x squared is odd.
nope, P and not Q. Keep the P,
Okay.
negate the conclusion. See, because if P didn't imply Q, then P happened and Q failed to follow. That's why
Okay.
so 5x is
So
even,
5x squared is even
x squared is even,
and x is odd.
right. And we wish to get a
We wish to
contradiction.
show, we wish to get a contradiction.
So we have two things that we know. We know that 5x squared is even by hypothesis, and we know that x is odd. And the question with proof by contradiction is always, gosh, how are we going to get the contradiction? It's always a little bit more challenging than proof by contrapositive because we don't really know which of these we're going to run with and which of these we're going to contradict. But when in doubt, keep it simple. The simplest piece of hypothesis that we have is that x is odd. Let's run with that and see if we can contradict this. See
Okay.
what I mean?
Yes.
So since x is odd, and this is going to look a lot like the algebra that we just did. X is 2k plus 1, right? Where k is in
Yes.
z. And now we just run with this fact, this equation about x looking that way. And now we're going to look at 5x squared and see if we can show that this assumption forces 5x squared to be odd, and that will contradict our hypothesis that it's even. Does that make sense?
No, I'm a little bit confused.
Well, the point is this. If we're going to use our hypothesis that x is odd, which we're doing right here by writing this nice equation, we have to contradict something. Well, the only other thing going on is that 5x squared is even. That's part of our hypothesis. So the only thing we can really do with that now is to try to contradict it. See, we've already thought this through. What happened before when we assumed x was odd? What happened with 5x squared in our proof by contrapositive? What did 5x squared?
5x squared was odd.
Yes. So we can do the same algebra, look at 5x squared, show it turns out to be odd, and that will contradict this piece of our hypothesis. It's really the same work.
Plus 5.
Thank you. Yeah. Right? And since k is in z, j equals 10k squared plus 10k plus 2 is in z because z is closed under addition and multiplication. That's another way to say that sums and products of integers are integers. You can talk about z as a set being closed. So 5k squared does equal 2j plus 1, where j is an integer, making 5x squared odd, right?
Yes.
But we assumed 5x squared is even. So this is our contradiction. This contradicts our hypothesis that 5x squared is even. And that's the way we would write a proof by contradiction. See, we
Okay.
conclude the negation is impossible, so the original must be true. So they're very similar in terms of the algebra, but it's a little more mysterious to write a proof by contradiction because you might not always actually see what that contradiction is going to turn out to be.
Okay.
Now, one of the main kinds of statements that we have to use contradiction for are statements like this, statements involving one rational and one irrational, like in homework 8. You always want to prove these. By contradiction, not contrapositive, but contradiction. So definitely look at that playlist because I have some special topics lectures, which is maybe the lecture you missed. I don't know. Did you miss the lecture when we proved that the sum of a rational number and an irrational number is always irrational?
So I missed the first lecture about that. The one I came for was the one we had on Thursday.
I can't remember exactly which one that is.
Sorry, on Wednesday. When we came in and we did it, you went over it again. Then we had to start doing like practicing homework 8, special homework 8 in class.
So for all real x and y, here's a statement. If x is rational and y is irrational, then x minus 2y is irrational. Okay, you're going to want to prove that by contradiction. Okay, this is our p of xy. This is our q of xy. We're trying to prove if p, then q. And it's really hard to try to prove this directly. And the reason it's hard to prove directly is because if we just assumed that x is rational and y is irrational, and that we wished to prove x minus 2y is irrational, how do we even show something is irrational? You see, the definition of irrational doesn't give us any nice equations to satisfy or to show, something is irrational. We just don't have enough to work with. Yeah, we've got an equation for x being rational if we assume p, but we got no equation for y because it's not rational, so we get nothing there. And then our wish is to show something is irrational. Well, we don't even have a way to show something is irrational because the definition of irrational doesn't involve any equation that we could satisfy. For example, if we're trying to show something is odd, we know we have to get that object.
2k plus 1.
Yeah, but we got nothing like that to show something is irrational. You see what I mean?
Yes.
So if we write the negation, it says there exists real x and y such that p of x, which is that x,
X is rational
mhm,
and Y is irrational.
good, that's our p of x. We keep p of x just like it is. And, of course, because the negation of an if-then is an and statement, and it's going to be not q of xy.
Then 2x minus 2y is rational.
Yeah, it's not a then, it's an and. Now let's take a look. If we assume this, then suddenly we've got a lot more to work with. We're going to have an equation because x is rational. Well, we're going to have an equation because x minus 2y is rational. So we're going to have two equations. Now, it's true, we do not get an equation from y is irrational. Y being irrational doesn't give us an equation, but this is something we'll be able to contradict. Because
So do we have to so since we don't have an equation for y, so we just leave y alone?
and later we're going
And
to use this information and contradict it. That's the
okay.
way we use this. So for now, we leave it alone, but eventually we're going to solve for y using this equation and that equation, and these two are going to force y to be rational, and that will contradict our hypothesis that y is irrational. That's how we use this bit. We contradict this bit. It's the only way we can use it because it doesn't give us any equation. There's nothing else we can do with it but contradict it. So let's assume, the whole negation. There exists x and y in the reals such that x is rational, y is irrational, and x minus
X minus 2y is rational.
exactly. And what do we wish?
We wish to show wait,
The
we
wish is
wish to show that x minus 2y is rational.
no, that's hypothesis. We
Oh,
don't wish to show that. What we wish to show is a contradiction. We wish to show a contradiction. The wish is always the same in proof by contradiction.
okay.
We always wish to get a contradiction. So now we've got that x is rational, and we've got that x minus 2y is rational. We can write an equation for each of these, right? So by the definition of rational, what is x? What do we get since x is rational? You tell me.
Um, what's the definition of rational again?
It's
It
a
has
quotient.
something to do with wait, something not b is not equals to 0. I can't remember the first part of it.
Well, the first part's pretty important. X equals A over B. Second part is important.
It's where b is not equals to 0.
Well, that's the third part. But
Okay.
before we say what B is not, it's polite to say what B is. B is an integer, okay? So part
Okay.
one is that X equals A over B. Part two is that A and B, I mean, we've introduced these new variables. We need to tell the reader what they are. They are in the integers. They are integers. And then B is not 0. And now we're going to get another equation because x minus 2y is also rational. So x minus 2y equals, I don't know,
A over b.
we can't use A and B again. We already used
Sorry,
them.
c over d.
Yes, C over D, where C and D are integers, and you can give me the last part because you know it well.
And b, I'm sorry, d is equals to 0.
Not
Is not equals to 0.
perfect. So now we've got these two equations about x and about x minus 2y. We've got information about A, B, C, and D. And we've got these caveats that tell us what B and D can't be. So we're going to use all 6 pieces of that information. What we didn't use yet, we didn't use this bit of
Why?
hypothesis that it's irrational, but we're going to contradict that. That's the only way we can use that. So here's my little word of advice. We have an equation about x. We have an equation about x minus 2y. Take the bigger equation, the bigger expression, and set it equal to itself. Surely nobody will argue that x minus 2y is equal to x minus 2y. Nobody's going to argue with that. It's a tautology. It's always true, no matter what x and y are. Well, we can plug in for x, and then we can plug in over here for the whole thing. So x is a over b, right?
Yes.
Minus,
Minus 2y equals to
what do we know about x minus 2y?
x minus 2y is c over d.
Great. And now we can solve for y. We've got minus 2y equals cd minus a over b. So we've got minus 2y equals cb minus ad over common denominator bd.
bd.
And so finally, we can just divide both sides by -2, and we can get CB minus AD. Or you could put AD minus BC over 2BD. It doesn't matter. The point is we've got Y looking like something over something. And we'll be able to argue that both the numerator and denominator are integers because A, B, C, and D are integers. And we'll be able to argue that minus 2BD is not 0 because B is not 0 and D is not 0. And of course, -2 isn't 0 either. And that way, we're forcing Y to be rational, and that's going to contradict our hypothesis that Y is irrational. See how it goes?
Yeah.
So let's hit part 2 of the definition of rational, right? Since A, B, C, and D are integers, see, differences and products of integers are integers because we're using a difference here and
Okay.
products here. We can call the top M equals CB minus AD is in Z, and the bottom we can call N is -2BD is in Z. So we've got both the top and the bottom, numerator and denominator of Y are integers. Finally, we just talk about N, and -2BD isn't 0 because since B is not 0 and D
And
is
d
not,
is not 0.
yeah, and of course -2 isn't 0 either. You can say that, but you don't really have to.
Okay.
-2BD is not equal to 0. So in fact, Y equals M over N, where both M and N are integers. We did that here. And N is not equal to 0. N is -2BD. So Y is rational. And that contradicts.
The original statement.
Well, we're going to be more specific than that.
Okay.
Exactly what part of our hypothesis. Let's look at our hypothesis here. This was our hypothesis, very top.
Hmm?
Our hypothesis was that x was rational, y was irrational, and x minus 2y was rational. So what exactly are we contradicting?
Y is irrational.
Exactly.
You ready?
All right. So we conclude the negation is impossible. So the original statement must be true. And see, this is one of those that you really can't do by contrapositive. You really can only prove this one by contradiction. Any kind of
Okay.
statement, any statement involving one rational and one irrational, you want to attack with a proof by contradiction. And in special homework 8, problem number 2 was some expression that involved square root of 2. And you're going to want to attack that with contradiction as well. Let me just take a look. at that particular statement. Let me just grab the special homework. Number 8, it's just a couple of problems. But number 2 was it was for all real x. If x is rational, then the number 3x minus 7 square root of 2 is irrational. And you were told square root of 2 is irrational and that you can use that fact. So instead of a y for our irrational,
We have a root 2.
root 2 is like the y. So basically, assume the negation, again,
Which
we have
is for all x.
exists to x.
Sorry, there exists an x such that x is rational and 3x minus 7 root 2. Wait, 3x minus 7 square root 2 is
That-
rational.
Yeah. And then solve for square root of 2 and show this forces square root of 2 to be rational. And that's going to be a contradiction because we know square root of 2 is irrational. So that's the way that you work that one. Are you still there?
Yes, oh, sorry.
Okay, no,
Yeah,
you're
I'm still
fine.
here.
Okay,
I'm still here.
well, my friends, it's getting pretty late. So, Isaiah, I just wanted to ask, did you have any other questions or something that you really wanted me to address before?
No, I didn't have any. I'm good.
You did? All right, well, work on homework 8. That should give you lots of practice. And make sure you did homework 7, right, Divine?
Yes, I already submitted homework 7 and 6.
Well, that's all well and good, and I'm grading 7 now.
Okay.
And I'll post the solutions to 8 on Tuesday night.
Okay.
All right. All right, I'm gonna get these 9 pages. Oh, we've actually got 9 pages of notes. We did a lot tonight. I want to get them posted and get the recording up, okay?
Okay, thank you so much.
Thanks for playing, guys. I'm glad you were here.
Of course.
Good night.
No.